Good evening to you all.
Good evening. Good evening.
Good evening. Continue from the yesterday's lectures. Yesterday we discussed about the central limit theorem. The central limit theorem says about the sampling distribution of the mean, right? So if a random sample, we are selecting a random sample of size n from a population. We don't have any knowledge about the population distribution, right? Whether it's a normal distribution or non-normal distribution. But we say that its mean is mu and the standard deviation is sigma. Then when n is sufficiently large, the sampling distribution of x bar, right? The sampling for any statistic, we are looking at the probability distribution for any statistic. That's called as a sampling distribution. Why here we are saying it's a sampling? Because this mean is calculated from the sample observations. Right? So for sufficiently large sample size, this mean has a normal distribution with parameters mean, that is denoted by this one, that's equal to population mean, and the standard deviation, that is denoted by this notation, that's equal to sigma over square root of n. Right? So when the sample size getting large, the standard error also getting small, and it more better approximation for the normal distribution. So for any population, when we are taking a sample size of n and n is enough large, then the sampling distribution of x bar has always the normal distribution with a mean that is equal to the population mean and the standard deviation that is equal to sigma over square root of n. Right? So any probabilities, if you want to calculate with a sample mean, in terms of sample mean, then this central limit theorem is very useful to calculating the probabilities. This is already been seen in the yesterday class. And then how large the sample size. For most of the distribution, whatever your population distribution, n should be 30 or more than 30, will give a sampling distribution nearly normal. But for any normal population is any normal distribution, then the sampling distribution also normal regardless of the sample size. For the unknown, if your population distribution is unknown, then you have to look at your sample size. But if your population is normal distribution, then there is no need of looking at the sample size. The sampling distribution of x bar is always normal. Right? These 2 points are very important to calculate the probabilities related to the sample mean. This example yesterday we seen. Anyway, again I will explain this example. So here a population has mean mu is equal to 8, sigma is equal to 3, right? Here there is no any information about the population distribution. Only we know the mean and the standard deviation. Then we are taking a random sample of size n equals 36. Right? Now we want to calculate the probability that the sample mean, right? Here mentioned that for which random variable we are taking to calculate the probability for the sample mean. That is between 7.8 and 8.2. So usually when we are calculating the probabilities, we have to know what type of distribution our population has, right? But in this case, we want to calculate the probability related to sample mean. But we don't know the probability distribution for sample mean. So now from this one, we have to get the idea what is the probability distribution for sample mean. But here we know that the population distribution is unknown, but the sample size is greater than or equal to 30. And also we are calculating the probability related to sample mean. So here we can apply the central limit theorem. Right? So now we apply the central limit theorem. Right? So from the given problem, we have the following data. Population mean is mu, that is let x is a random variable. There is no any information regarding what is x, but just we are taking x is a random variable. And then for this random variable, the mean is mu. Mu is equal to 8 and sigma is equal to 3. So the distribution of x is unknown. This distribution of x is unknown. And also from this population, we are taking a sample of size 36. So now x bar is sample mean. Right? So, and also we need to calculate the probability that the sample mean is between 7.8 and 8.2. So in the notation form, probability of 7.8 less than x bar less than 8.2. If you want to calculate this probability, now what is the probability distribution of x bar? To calculate the probability, we need what is the probability distribution of x bar. Right? So because here population, we have the information to decide the distribution in greater than or equal to 36. Is equal to 36. And also our probability is related to sample mean. So as n greater than or equal to 30, the sample size greater than or equal to 30, according to central limit theorem, we can say that x bar has a normal distribution with mean. If we specify the normal distribution, then the two parameters we have to specify. One is the mean of the normal distribution and the standard deviation of the normal distribution. With mean mu x bar, that is equal to our population mean mu, that is equal to 8. and standard deviation. Sigma x bar is equal to sigma over square root of n, where sigma is 3 and your n is square root of 36. That is 1 over 6, 3 over 6, that is half. That is 0.5. That is, now we can specify in the notation form, that is x bar as a normal distribution with mean 8 and your variance 0.5. Now we can calculate the probability, right? So now we are taking the next slide. Calculate the probability. Now from the previous slide, we have x bar, the normal distribution with mean 8 and the variance 0.5 holding square. And we need the probability 7.8 less than x bar less than 2. Now we have to convert this one to the standard normal, right? Because if you want to calculate the normal probabilities, we have to apply the standard normal table. So according to this distribution, now we have to convert the standard normal distribution. So now we will convert if x bar equals 7.8, then z equals x bar minus mu over sigma over square root of n. Because for a standard normal distribution, sampling distribution of x bar, the standard error is a standard deviation that is given by sigma over square root of 8. So where x bar is 7.8 and mu, that is 8 minus 8 divided by sigma over square root of n, that is 0.5. So that is equal to minus 0.4. Similarly, our next boundary point, if x bar equals 8.2, then z equals x bar minus mu over sigma over square root of n. So 2 minus 8 over 5, that is equal to 0.4. So now we have our x bar values in terms of z value. So now the probability of 7.8 less than x bar less than 8.2 equals probability of, for 7.8 we have z value minus 0.4. Instead of x bar, now we have z. Now if we have a diagram for this one, if it's a standard normal, then the mean value is 0, then 4.4, and minus 0.4. This shaded area we have to have. So that is equal to this plus this, probability of minus 0.4 less than z less than 0, plus probability of 0 less than z less than 0.4. But symmetrical, this is also same as probability of 0 less than z less than 0.4 symmetrically, plus probability less than z less than 0.4. That is equal to 2 into probability of 0 less than z less than 0.4. That is equal to 2 into, from the table, 0.1554. 0.1554. That is equal to 0.3108. That is 31.08%. So what is the interpretation for this one? 31.08% of the mean values, right? Mean values will fall between 7.8 and 8.2. Right? 31.08% of the mean values will be between 7.8 and 8.2. Right? Now we will move to the next exercise. It's regarding cellular phone bills for residents of a city have a mean of rupees 630 and a standard deviation of rupees 110. Right? So now it's regarding the phone bills amount. Right? We are talking about the phone bills amount. So next, now we are going to define the values. Let X that denotes the phone bills amount, right? Phone bills amount. Then it have a mean, right? So mu x, that means this variable, the mean value is 630 and the standard deviation sigma x equals 110. Just we are denoting what the variable we have, right? And also they are taking n is equal to 100. That 100 phone bills they are taking, right? And the mean of each sample is determined. Now we have to find the now that. So for E x bar, that is mean amount. Let x bar mean amount of phone bills. Find the mean and standard error of the mean of the sampling distribution. Right now we have to find what is mu x bar. That is mean of the sampling distribution. Mean of the sampling distribution and the standard error of the mean of the sampling distribution. Right? What is mu x bar? So standard error of the mean of the sampling distribution is standard deviation. That is sigma x bar. This is mean of x bar. It is standard error of x bar. These two things we have to calculate, right? But we don't have any knowledge regarding the population. Here population is denoted by x. This population we don't have any knowledge, but only we know what is the phone bills amount mean and what is the phone bills amount standard deviation. Now we have to get the mean amount of phone bills. For this distribution, what is the mean value and what is the standard deviation value? These two things we have to calculate. So now we have to look at our sample size. If we sample size if you know the sample size, then we can apply the central limit theorem. So now n is equal to 100. So as n greater than or equal to 100, sorry, as n greater than or equal to 30, according to central limit theorem, x bar, what is the sample x bar has a normal distribution. Where mu x bar, that is mean of the sample x bar, that is equal to population mean, right? According to the central limit theorem, that is equal to population mean. How the population mean is given here 630. Right? One thing we have. The error, that is sigma x bar, is equal to sigma x over square root of n. Sigma x is 110 over square root of sample size 100. That is 110 over 10. That is 11. Right? Now we identify these two things. What is the mean of the sampling distribution? Right? Then standard error of the sampling distribution. Right? So sampling distribution mean is mean of x bar, and the standard error of x bar is standard deviation of the sampling distribution. Then sketch a graph of the sampling distribution of the sample means. The graph of a. So now we say that x bar has a normal distribution. Then the graph is as it is a normal distribution. Here your x bar, it has a symmetrical bell-shaped curve. And this is your mean value. X bar, that is 630, and the sigma x bar is equal. This is a way of answering the question. So if we are talking about the sampling distribution of X bar, then you have to decide how we are saying that it's a normal distribution. Here also, based on the sample size, because our sample size is 100, so n greater than or equal to 30, right? So from which we can say that it has a normal distribution. So if it's a normal distribution, then what is the mean value and that is the standard deviation value both here, right? Now we move to there are two exercises. I will explain each and every exercise, but you have to complete the answers, right? First question. Long distance telephone calls are normally distributed. Here they specify the distribution. The long distance telephone calls are normally distributed. What is the mean value? 8 and the standard deviation 2. If you select a random sample of 25 calls, what percentage of the sample means? The probability is related to sample mean, right? What percentage of the sample means would be between 7.8 and 8.2. So now here the population is related to the duration of the long distance telephone calls, right? Duration of the long distance telephone calls. So now here we are taking a random variable X. Long distance duration of, or length or duration of distance telephone calls. They say that X has normal distribution. X has a normal distribution with mean 8 and the standard deviation 2. And we are putting in the notation form, always we have to put the variance, right? Right. Now we are selecting a sample from this population. N is equal to 5. And let what percentage of sample means. So now we are defining X bar, mean duration, of the telephone calls, long distance telephone calls, right? And they want to calculate the probability percentage. Sample means would be between 7.8 and 8.2. Probability of 7.8 less than X bar less than 8.2. For now, we have to calculate find out what is the sampling distribution of X bar. Sampling distribution. Sampling, that means probability. Distribution of X. Right? But here sample size is small. So we can't apply the central limit theorem. If you want to apply the central limit theorem, n should be 30 or more than 30. But here n is equal to 25. But our population has the normal distribution. So for any sample size, if the population is normal distribution, then X bar also normal distribution, right? So as X has normal distribution, X bar also has normal distribution. With mu X bar is equal to 8. And sigma X bar is equal to sigma over square root of n, where sigma is 2 and square root of n, sample size is 25, that is 2 over 5, that is 0. Right? Now we identify what is the sampling distribution of X bar. Now we are ready to calculate the probabilities. I'm going to take the next slide. You want to note it quickly. Right? Include another slide. Space is not enough. Right. So from the slide, we have X bar, which has normal distribution with mean 8 and standard deviation 0.4 square. And now we want to calculate the probabilities. Probability of 7.8 less than X bar less than 8.2. So now we have to convert in the standard normal. So if X bar is equal to 7.8, then Z is equal to X bar minus mu over sigma over square root of n. 7.8 minus 8 divided by 0.4. That is equal to minus 0.5. Similarly, x bar is equal to 8.2, then z is equal to 8.2 minus 8 divided by 0.4, that's equal to 0.5. So now our probability of 7.8 less than x bar less than 8.2 is equal to probability of minus 0.5 less than z less than 0.5. Right? So according to the graph, if we have a graph for this probability statement, it is z 0, here 0.5, here minus 0.5 is shaded area we need. From the symmetrical, this is equal to 2 into probability of 0 less than z less than 0.5. Right? I think it is into 0.1915, that is equal to 38.30%. Then how you can interpret it? I'm writing the interpretation over here. Uh, 38.3% of the means, percentage of the means. Here we are talking about the x bar, right? So 38.3% of means of length of telephone calls, means of lengths of telephone calls will be 7.8 and 8.2. So always when you are writing the interpretation, you have to relate the interpretation to the problem. Right? You can't write the general interpretation. Always you have to relate the explanation of your figure you got. With the problem. Right? The next example. The weight of a particular chocolate. Right? Here they are talking about the weight. Has mean of 12 gram and the standard deviation of 0.2 gram. If you select random samples of 50 chocolates, what percentage of the sample means would be 11.95. So here we are defining X, weight of a chocolate. X denotes the weight of a chocolate. Then it has a mean of 12. So mu X equals 12 and sigma X equals 0.2, 0.2. A random sample of 50 chocolates. N is equal to 50. Then you have to calculate the probability related to sample mean. So we are taking X bar, mean weight of. If you want, you can mention the sample size also when we are defining the sample mean weight of 50 chocolates. X bar denotes the mean weight of 50 chocolates. And they are asking to calculate the probability of X less than 0.9. So now we have to specify the population distribution, sampling distribution of X bar. But the population distribution is unknown, but the sample size is 50, right? So the sample size is greater than 30, right? So here we are going to apply the central limit theorem. The sample size as n greater than 30. According to central limit theorem, X as a normal distribution, right? With the mean, population mean 12, and the variance or standard deviation sigma over square root of n, 0.2 over square root of 50. This mean X bar is equal to 12 and sigma X bar is equal to 0.2 over square root of 50. So now you can calculate the probability using the standard normal. So now X bar less than 11.95. So first we have to get the standard normal value. So if X bar equals 11.95, then Z is equal to X bar minus mu over square root of n. So here X bar is 11.95 minus mu is 12 and this is 0.2 square root of 50, right? Now you can continue this one, okay? Right. Now we will move to the next example. There is two parts in this question. It's related to the credit card balance, right? Credit card debts carried by undergraduates are normally distributed. They say that the credit card debts are carried by undergraduates are normally distributed with a mean of 3,173 and the standard deviation of 120. So, application is regarding the credit cards, loans, so balance, credit card balance has normal distribution already. It has a normal with mean 3,173 and the standard deviation. Now, you look at these two questions are different, right? What is the probability that a randomly selected undergraduate who is a credit card holder has that's only, it is a mean, it is a credit card balance that is less than 2,700. So using this information, now the credit card balance has a normal distribution with mean 3,173 and the standard deviation 1,120. We can calculate the probability that credit balance is less than 2,700. In the second part, they are randomly selected 25 undergraduates who also credit card holders. Then what is the probability there? Here, mean credit card balance. Now you look at these two questions. Here, there is no mean word, right? There is no the term mean, only credit card balance. But in this question is related to mean card balance, which is less than 2,700. So these two questions are different. So here we have to look at the probability distribution of X bar, but here we are looking at distribution of X. Right? This difference you have to understand when we are asking to calculate the probabilities. Right? So now we will go one by one. So according to this one, now we define X. Credit card balance. Balance of credit card balance, right? And they say that it has normal distribution with mean 3,173 and the standard deviation 1,110. So if you specify the variance, that is, and we want to calculate the probability because only they are asking the credit card balance. So it is related to the random variable X. So probability of X less than 2,700. So now corresponding Z value we have to calculate. So if X equals 2,700, then Z equals X minus mu, sorry, not X bar, right? X minus mu over sigma. Not sigma over square root of X, because here we have the notation X. We are not considering about the mean, right? We are just considering about the credit card balance. So now X is equal to 2,700 minus mu is equal to 3,173 and sigma is equal to 1,120. From this, you can get the Z value and then use this Z value to calculate the probability, right? Now, the balance you can do it, right? Get the Z value and then how we perform in the previous slides, similarly you can do it after getting the Z value, right? the same example. And here you have to complete, right? Part B, the same question. But related to sample mean, right? So X already we defined credit card balance. And it has normal distribution with mean 73,120 squared variance. Right? Now they are selecting n is equal to 25. What is the probability that their mean credit card balance as a mean credit card balance? Credit card balance. Right? Then is 20. So the sampling central limit theorem we cannot apply because central limit theorem is only applicable for the N30 or the 30. But we know the information, it is a normal distribution. X has a normal distribution, right? So since X has a normal distribution, X bar also has normal distribution. Distribution with mu X bar is your population mean, that is 3,173, and standard deviation sigma X bar is sigma over square root of n, that is equal to 1,120 divided by square root of 5. That is 5, so 224. Right. Now, what is the probability? Balance is less than 2,700. So, probability of X bar less than 1,700. Yeah. Right. So now here also we have standardization. So if X bar equals 2,700, then that equals X bar minus mu over here sigma over square root of n, because we are using X bar. That is 2,700 minus mu 3,173 sigma over square root of n 200. From this you can get that value, and then you can calculate the right. So now we completed our sampling distribution of X bar, right? So this one you completed. Now another sampling distribution, we want to look at the proportion, right? These two sampling distributions are important. For the next lessons, we are going to learn about the confidence interval estimation and the hypothesis testing, right? So what is proportion? Here we are using the population proportion P, or somewhere we can use as a capital pi. Either one of the notation we can use, P or pi. So the proportion of the population having some characteristic. Now we are saying that define P is the proportion of the population having some characteristic. Then in the sample proportion, this is the population proportion. The sample proportion denoted by P hat, that is equal to X over N. Here X is the number of items in the sample having the characteristic of interest divided by the sample size. So here, suppose we are saying that we are looking at the defectives of a particular items, defectives of particular items in the population. We are looking at the defectives of particular items in the population. Then from that population, we are selecting a sample of size n. We are selecting a sample of size n and observe that how many items in that sample are defective. That is denoted by X. We say that X number of items are defective out of n items. So X is the number of items in the sample having the characteristic of interest. Here we are looking at the defective. The characteristic of interest is defective. Then how many sample size we took? N. But always when we are calculating the sample proportion or population proportion, both are in between 0 to 1, including 0 and 1. Then what is the sampling distribution of P hat? The P hat is our sample statistic. That is the sample proportion here. So for this one also, when samples are different samples, we will get the different values. So the P hat, there is a variability in the P hat sample to sample. Like a same pattern, meaning in the sampling distribution of X bar. We generated different samples and for each sample we calculated the sample weight. Here also from the population, we are taking different samples and for each and every sample, we are calculating the P hat. So here also for large sample size, this P hat has a normal distribution. The P hat is approximately normally distributed. This is the graph, right? Here we are taking P hat and this is the probability of P hat. So for every sample, we are taking the P hat and we are plotting this one, then this kind of graph you will get. This is also approximately normal distribution. So what is the mean value? What is the population proportion you have? That will be the mean value. The population proportion is the mean value of this sampling distribution. And the variance is given by P into 1 minus P over N, where P is the population proportion, right? Then, according to the, because this P hat, that is sample proportion, is also has a normal distribution, then how we can make the standardization, that is P hat minus P divided by sigma over P hat, where P is the population proportion and this is the N is the sample size, right? So to make the standardization, because our mean value is P, right? And the variance is P into 1 minus P over N. So that is variance, square root of variance is the standard error that is denoted by sigma over P hat. That is square root of P into 1 minus P over N, right? So this formula you have to use when we are calculating the probabilities related to P hat, right? So now we are taking a simple example. If the true proportion means population proportion. If the true proportion of voters who support proposition A, right? A firm it proposed something strategy or something that is named as proposition A, and we are looking at the proportion of the waters. How many waters are supporting this proposition? So the population proportion is 0.4. That means 4%, 40% of the voters who are supporting the proposition A. This means 40% of the supporters, voters who are supporting proposition A. Then what is the probability that sample of size 2000, we are taking from these voters, only 200 voters we are selecting, and then we are looking at what is out of this one, what is the probability that a sample of 200 yields a sample proportion between 0.4 and 0.45. So when we are putting this statement in the notation form, they gave that P is 0.4 and N is 200. And what is P hat? Here they are looking at sample proportion. This is between 0.4 and 0.45. Right? So based on the previous slide, we have, it has a normal distribution, right? Now here we mentioned the distribution. Now we need what is the distribution of P hat. If you want to calculate this probability, now we need what the distribution of P hat. What is the probability? Oh, this is also a statistic. So sampling. Because these values we are obtained using the sample. So sampling. What is the probability of sampling distribution? P hat. So based on the previous slide, P hat has normal distribution. Me, that is the mu P hat. Now instead of x bar, now we have P hat. Mu P hat. That is equal to population proportion P and sigma standard deviation or standard error of P hat, that is square root of P into 1 minus P over. Now we know P is equal to 0.4 and N is equal to 200. It has a normal distribution from the previous slide, right? So now according to that, calculate sigma P hat is equal to P into 1 minus P over N. That is P is equal to 0.4 and N is equal to 200. So from this you got this value. Right? Then to convert the standard normal, so Z equals P hat minus P over sigma P hat. That is P hat minus P over sigma P hat is this one. Right? So that is equal to P hat minus P is 0.4 divided by Z equal to 0.3464. So now our probability is this one. So when P is equal to 0.4, if P is equal to 0.4, then your P, sorry, if P hat is 0.4, then Z is equal to 0.4 minus 0.4 divided by 0.3464, that is 0. Then if P hat equals 0.45, then Z is equal to 0.4 minus 0.45 over 0.3464 to 1.4. Right? That one. Then, as usual, what is the standard normal table? From the table, you can get the value. So now both diagrams here we mark. When P hat is 0.40 mean value, it is 0.5. And when we are converting to standard normal, 1.44. So from the table, 0.4251, right? So that is for 0.4251. What is the interpretation? This means, here I am writing the interpretation. Sorry, 42.5% of waters who will support, no? Who support proposition A. Will be 0.40 and 0.45. Right? 42.51% of the waters who supporting the proposition A will be from these two values. Right? We completed this sampling distribution, right? So any doubts in the sampling distribution? So now we start the next session. Is the slides visible? Confidence interval estimate?
Yes.
Right. So the next section, we will start the introduction part today. Right. So now, actually, so far, when we are calculating the probabilities, we look all our population parameters are known. Based on the non-population parameters, we calculated the probabilities. But in the real life, it's very rare situation. The population parameters are known. Specifically, the mean and the standard deviations are unknown for the population. Right? So now, how we can estimate these unknown population parameters, mean and the standard deviation, or the proportion, mean, the proportion and the standard deviation, how we can estimate when these parameters are unknown. Parameters, when we are talking about using the term parameters, that means we are talking about the population, right? So here, two types of the first thing we are to estimate, we are looking at the confidence intervals. Actually, to make the decision related to the population parameters, because in the real life, we say that these population parameters are unknown. So we want to make the decision related to this population parameters. There are two main techniques we can apply to make the decisions regarding the population parameters. One is the estimation and other one is the hypothesis testing. Estimation is one section and the hypothesis testing is another section. So here first we are looking at the estimation theory. In the estimation theory, two types of estimates we are looking at. One is the point estimate, other one is the confidence interval estimate. The confidence interval estimate is depending on the point estimate, right? So here, in your syllabus, we are using the estimation procedure for the population mean and the population proportion. The two things we are looking at. One is the how we can estimate. That means we have to find the approximated value for the population mean and for the population proportion. The finding the approximated value is called as an estimation. But this approximated value we are going to find from using the samples. Right? So these two parameters we are going to estimate. Population mean. The population mean under two different situations we want to estimate. One is population standard deviation is known. The other thing, population standard deviation is unknown. So when sigma is known, how we can find the value for mu, and sigma is unknown, how we can find the value for mu. Then another parameter we are looking at proportion. So how we can find the values for population proportion. Then if we want to estimate these values, what is the sample size we need? That is also important. If you want to estimate the mean or proportion, then what is the sample size we have to take? These three things we are going to looking at under the confidence interval section, right? So what are the learning outcomes we have? You will be able to, at the end of the session, you will be able to construct and interpret confidence interval estimates for the two parameters, mean and the proportion. And also, you will be able to determine the sample size necessary to develop a confidence interval for the mean or proportion. So, 4 parts here we are going to study. One is how Right. So you will learn how we can construct confidence interval estimate for mean, how we can construct confidence interval for proportion. Here 2 parts. And then we have to decide what is the sample size we need to construct confidence interval estimate for mean, and what is the sample size we need to construct confidence interval for the proportion. So 4 parts here we are going to learn, right? So using statistics in the workplace, right? So here how we can relate our estimates to the real life case, right? So here there is a Raja Home Improvement Distributors. They are distributing home improvement supplies in the country, right? So this is a company. For this company accountant, he is responsible for accuracy of the integrated investment and the sales information system. For these 2 systems, how these 2 systems are work. For this, to find out these related issues, this company accountant is responsible. How this inventory management is working properly, and also how the sales information system also working properly. So to look at, so to determine the accuracy of this system, the company accountant, he is going to review the contents of each and every record to check the accuracy of the system. So what is the bill they produce, then inventory management records and everything, the accountant has to check to identify the accuracy of the integrated system, right? But for each and every day, there are, because it's a very big company, then there are a very large number of records will be there. So it is very difficult and also time consuming and the cost if you want to review each and every records in detail. Okay? So based on the time consumption and the cost, what we can do, we have to use the statistical techniques. So the better approach is to use statistical inference techniques to draw conclusions about the population of all records, right, from a relatively small sample collected during an audit. So using during the audit time, they can take a sample, 30 or 40 or 50 samples records, and by looking at those records, then they can estimate the accuracy for the whole system of records, right? This is the main task. So here, the main statistical inference, the main part is we have to make the decision for the population based on the sample. That is the beauty of the statistical inference. For the statistical inference, we don't need to consider whole population. Just we are taking a part of the population, and from that part of the population, right, we have to make the decision based on the sample to the population, right? So how they can use that information at the end of each month, right? A sample of sales invoices would be selected. This is the method how they are going to measure the accuracy for the full system. For each and every month, they are selecting a sample of the sales invoices would be selected. And from these sales invoices, they can find out the mean amount listed of the sales invoice for the month, how much of sales occurred, right? And also the proportion of invoices that contain errors. So actually, if you want to check the accuracy of the system, we want to find out the invoices, the errors that contain in the invoices, right? Which violate the internal control policy of the warehouse. They have a internal control policies they have. So regarding that internal control policies, what are the errors, or by violating, what are the errors in the invoices have. By using this mean and the proportion, then we can determine the accuracy of the inventory control system and the sales system, right? So after finding these two values, then how accurate are the results from the samples and how we can use this information. This is the part we are going to learn. And also, are the sample sizes are large enough to give the information that is needed, whether with our sample size, whether the sample size is enough to provide the accurate information related to the accuracy of the system, right? So this is the method we are going to learn with our examples, right? Point and interval estimates, right? A point estimate is a single number. In the estimate, there are actually two types of estimates are there. One is the point estimate and other one is the interval estimate. So the difference between the point estimate and the interval estimate, point estimate is a single value. Only one value will be there. But in the interval estimate, it will consist of a range of values as an estimate, right? Interval estimate consists of infinite number of range of values it will consist. So if you're looking at this diagram, now only one point, this will be a point estimate. And if we consider all these values within the lower limit and the upper limit, that is called as an interval estimate. If we are providing the interval estimate, then these are each and every value within that interval is possible as a point estimate, right? Each and every value within this interval is possible as an estimate, but point estimate provide only one single value, right? So comparing these two estimates, the more accurate estimate is an interval estimate. So the interval estimate, because it provides more infinite number of possible values for the estimates for the population. So it is more accurate comparing to only one single value as a point estimate, right? So the lower value of this interval is called as a lower confidence limit, and the upper value of the interval is called as an upper confidence interval limit, and within this interval is called as a confidence interval, and the length of or the width of this interval is called as the length of this interval is called as a width of the confidence interval, right? So usually, because here we are looking at only two parameters, we want to estimate the population parameter that should be estimated, mu, that is population mean. Here we are looking at notation pi, that is population proportion. So if these two are unknown, then we are going to take a sample, and using the sample results, we want to find what is the approximate value for this mu and what is the approximate value for this proportion pi. So as a point estimate, the sample mean x bar is the approximated value for mu, and the sample proportion p is the approximated value for pi. So the point estimate of a population mean is the sample mean x bar, and the point estimate of the population proportion is the sample proportion small p. So these two proportions, these two values are the point estimates, and it is a statistic, sample statistic we are using as a point estimates, right? Then, because only one sample we are using, based on that one sample, we say that this is the approximated value for the population parameter. So here we are not Because when sample to sample, when we are taking the different samples, the X bar also will be different. When we are taking the different samples, the X bar or P proportion, both will be different. But when we are looking at the point estimate, we are not giving any uncertainty, because sometimes this will not be a true value, right? Because if our sample is wrong, right, we selected a biased sample, then our estimate will not be a true value. So how much of uncertainty is associated with the point estimate of a population parameter? By using this point estimate, we can't give any answer for this uncertainty. So to overcome this uncertainty problem, we are talking about the interval estimate, right? We are talking about the interval estimate. This interval estimate provides more information about the population characteristic than a point estimate, because there are infinite number of possible values will be there as a point estimate. So many approximators will be there, then mostly there will be a more chance to get the approximated population parameter value within that interval, right? So this is the better estimate comparing to the point estimate, because it provides the uncertainty to what extent our estimate will have an uncertainty with the population parameter. So such interval estimates are called confidence intervals, right? So confidence interval estimate, this gives a range of values, right? Infinite number of range of values. And also it takes into consideration variation in sample statistic from sample to sample, because there are infinite possible values will be there within that interval. So it giving some variation from sample to sample. When sample to sample, we have get different values. So that will be accommodated within this range of values. But these range of values are only based on one sample. We will not take so many samples, right? Based on the one sample, we are giving the variations for the from statistic sample to sample. That is the beauty of this confidence interval. Only based on one sample, we will calculate the confidence interval, and that confidence interval provides infinite number of possible values as an estimate for the population mean or population proportion, right? And also it gives information about the closeness to unknown population parameter. To what extent the closeness of the unknown parameters, to what extent it is close to the unknown parameter. But this closeness is stated in terms of level of confidence, right? This closeness is in terms of level of confidence, but this level of confidence cannot be 100% confident. Because why? Only we are depending on the one sample. So this still the level of confidence is not 100%. Right? This is the characteristic of confidence interval estimate. So the estimation process, how we are doing the estimation, right? So now we say that we have a population. This mean mu is unknown, right? So now we want to find what is the appropriate value for this one. So from this we take a sample, right? From the using the random sample technique, we take a sample, and from this sample we calculate X bar is as 50. Right? This is the point estimate of mu. This 50 is a point estimate mu. Right? Then using this point estimate, now we say that it is 95% confident that the mu is between 40 and 60. Based on this 50, we say that mu is between 40 and 60. From this, we say that mu is 50. We say from this 50, we say that mu is 50. But from this estimate, we say that mu is in between 40 to 60. So there are so many possibilities are there. It may be 40 or 41 or 41.5 or 50 or 52.5 or 60 or 59.5 or 52.8. So such an infinite number of possibilities are there. So 95% we can say that mu is in between 40 to 60. So this is point estimate. This is confidence interval estimate. Right? Suppose now we want to say that we want to find out the average marks of a first year student, business statistics average mark of a first year student, from the last batch. The last batch nearly say that 1,000 students set the exam. So we want to quickly find out what is the average marks. Then from the randomly, we are taking a 50 students. Randomly, we are taking a 60 students, right? And from those 60 students, we are collecting the marks and we say that that marks is 50. So from this, we are saying that the average marks for the business statistics of the last batch is 50. But to what extent this is accurate results? We can't say anything from the accuracy from this point estimate. So now we are saying that 95% confident that the average marks of a student for the business statistics is between 40 to 60. So here 95% we are saying that it will be in between 40 to 60. So it is more accurate comparing to this results. Right? So this is the concept behind on the confidence interval estimation procedure. Right? So the general formula for all confidence intervals is point estimate plus or minus critical value into standard error. What is the general formula? It is point estimate, right? This is we got from the sample. Critical value based on the sampling distribution of a statistic, based on the sampling distribution of X bar, or based on the sampling distribution of P hat. We can calculate the critical value. And the standard error also, from the sampling distribution, we can get the standard error. So the previous chapter knowledge is important to identify the sampling distribution of X bar or the sampling distribution of P hat. From that only we can get the critical value and the standard error. This is we can get from the sample. So this is the general formula for all, either mean or either proportion. This general formula we will use. This critical value we have to get from the table. This one we can get from our data. This also we can get from our data. Right? What is confidence level? This is measure the confidence, the extent of confidence for which the interval will contain the unknown parameter. What is the extent we are in confidence to say that our unknown parameter will fall in the interval. This confidence we are talking about in the percentage. We will talk about in the percentage. We can say that we are 95% confidence, or we are 80% confidence, or we are 99% confidence, right? In such manner, we can measure our confidence. So according to our confidence, this interval will be constructed. And from that, we can say that it will be in between two lower and upper values. Usually, we will take less than 100% because 100% we can't measure because we are taking only one sample. So based on that one sample, the 100% accurate confidence interval we cannot calculate, right? So suppose usually the confidence level is denoted by 1 minus alpha, right? Here this alpha is level of significance, right? you will be introduced this level of significance in the next hypothesis testing chapter, right? So usually normally we are taking our confidence level is 95%. So this is written as 1 minus alpha is 95%. So how we are interpreting in the relative frequency approach, how we are interpreting in the long run. That means when we are constructing 100 confidence intervals from the 100 samples, right? When we are constructing 100 confidence intervals from 100 various samples, then we say that 95% of all the confidence intervals that will contain the unknown true parameter. If we are saying that 1 confidence level is 95%, then that means 95% of all the confidence intervals. Suppose we are constructing 1000 intervals, then 950 intervals. If we are constructing 1000 intervals, then 950 intervals will contain the unknown true parameter. Right? But actually, a specific interval, if you are taking a single interval, either it will contain or will not contain the true parameter. Sometimes the parameter will be inside the confidence interval, but in few cases, it may beyond the confidence limits. So that's why this 5% error we are allowing. The 5% of the intervals may not contain the true parameter, right? 95% of the interval. The 95% means 95% of the intervals confidence, 95% of the intervals will contain the true parameter, and 5% of the intervals will not contain the true parameter. This is the meaning of level of confidence. Right. So this part we will start with tomorrow also. You have lectures from 4:30 to 6:30, right? So for the confidence interval with the population mean, we will calculate, right? For the confidence interval and for the population proportion. Under the population mean, when sigma is known, what is the confidence interval? When sigma is unknown, how we can construct the confidence interval for population proportion mean and for the population proportion. Population proportion only one case, but in the population mean, there are two different situations we are going to take. One is sigma is known and sigma is unknown, right? This is the two different confidence intervals we will calculate. So tomorrow, 4:30, we will meet. Any other doubts you want to ask? Right. So tomorrow, 4:30, you will have the link that will be uploaded in the